Hi, I'm here to talk briefly about the architecture that I've been developing over a few years with collaborators, as you can see, from different countries and with support from different agencies. This is primarily focused, of course, on integrating reasoning and learning. So let's look at some core ideas here. So the approach we are taking here is inspired by a cognitive systems formulation and from insights obtained from human cognition and control. The idea here is to represent reason and learn jointly at different abstractions using different schemes, but not to go for a unified representation or to go for a representation where there are separate modules that call each other, but instead have something in between that has a nice formal coupling between these different representations and reasoning schemes. So you could view this as a logician, statistician, and a creative explorer all existing together inside a robot. And they expect allow the robot, of course, to represent and reason, but also to interactively and cumulatively learn new concepts, right? So the idea is as you get more and more data, you don't start becoming slower. You somehow crystallize that into new concepts. And as a result, we have something that's a combination of knowledge-based reasoning, data-driven learning. Now, the attempt is to just give you a high-level overview. So if you look at this here, you have sort of a more coarser resolution where a logician performs a logical reasoning, non-monotonic logical reasoning about, say, in a domain with, say, different places and rooms. But at the same time, the robot is capable of refining this and selectively focusing its attention at a particular region at a higher resolution, right? As and when needed automatically. And to then you say do some form of probabilistic decision making as needed. Now, the key thing here is, of course, that for any given abstract transition, you can guarantee that there exists a sequence of transitions at a finite granularity, right? And here we are integrating the strengths of non-monotonic logical reasoning and probabilistic reasoning. But because this knowledge is incomplete, we also allow for some different kinds of learning mechanisms, right? That brings us to the interactive learning mode. As an example, if you were to take a robot that has to, say, manipulate objects and figure out which are occluded and which structures are unstable, one would normally take images and process them using some deep network architecture these days. But instead, we first try to do so with some form of non-monotonic logical reasoning. And if an answer is found, we stop there. If it's not found, the robot selectively looks at those regions where it's unable to give an answer, and you does learning only to address those problem cases. At the same time, because these problem cases could not be handled with reasoning, it tries to induce new concepts and new rules that can augment and revise the existing knowledge. So the next time around in similar situations, it doesn't have to use learning if possible. And we have also managed to combine this again into this architecture where it's able to provide relational expressions as explanations of its decisions and the evolution of beliefs over time. And also if the human wants it to explain something, but the question from the human is not clear, the robot is able to automatically construct a disambiguation query that helps it resolve these ambiguities. For more information, of course, please look at the paper. Thank you.